Good afternoon and welcome back to AIEC's Webinar Weeks. We're glad you decided to spend this afternoon with us. AIEC Webinar Weeks aims to address today's industry challenges and opportunities along with solutions and tips on how to overcome them. We've got a really interesting webinar here on wireless troubleshooting techniques. Before we get into that, a couple housekeeping items. Our presentation will last roughly 40-45 minutes. We'll leave 10 or 15 minutes towards the end for Q&A. Please remain muted for the duration of the webinar. And if you'd like to submit a question, we do ask that you do that through the chat function. You can select the drop down and direct those questions to AIEC. Those will come through to Brian and myself, and we will moderate those questions to the presenter on your behalf. Brian, I'm going to turn it over to you.
All right, our presenter today is Tisha Hayes. She is the senior engineer with 4RF USA. Her responsibilities include pre-sales engineering support, proof of concept testing, testing competing products in head-to-head bench and field conditions, and as a liaison to engineering and consulting firms. Tisha has more than 35 years of experience with wireless radio technologies, SCADA RTUs, instrumentation, process control, and cybersecurity for the electric, water, wastewater, and gas utilities. Most recently, Tisha was a principal at a Midwestern consulting company in their energy and utilities practice. One of Tisha's strengths is in the analytical approach of evaluating different wireless technologies and competing products in a lab setting that closely approximates field conditions under a variety of interference and propagation conditions while validating serial and Ethernet SCADA performance. So with that, I'll hand it over to you, Tisha.
Thanks very much for the introduction. Probably with this audience, it'll probably be helpful to note that that large consulting company I work with was out of Chicago, and I was embedded within Commonwealth Edison for about 3 years, doing their technology evaluations on their SCADA replacement and their distribution automation network. So that's how I originally came to 4RF, was through that association. Once I concluded that project with Commonwealth Edison, I switched companies to 4RF and I haven't regretted it at all. So I'm going to move forward from here with the presentation. Again, we're going to be discussing about wireless troubleshooting techniques. And while much of this is based upon the 4RF product, it is not exclusive. These skills are things that you can use for other wireless manufacturers. And I try to keep it as open in that regard as possible. And so I'll get started. Again, I'm a senior engineer with 4RF. I live in Alabama. I take care of North America primarily. But we have a service team of 3 other engineers, and I'm kind of like an escalation point for them on the really weird problems. Okay, so our objectives for today is, one of our biggest challenges usually is installing and maintaining a wireless radio network. And a lot of times this involves the process of us tracking down and identifying issues as they happen. This is not something taught in school. Engineers and technicians have to kind of acquire the ability to troubleshoot, a lot of times from on-the-job experience. So I'm going to try to put together as many of these little tricks into one presentation that's only an hour long. Now, really to get a deep dive into this would probably be 2 days of classroom with some hands-on. But we only have an hour to work with today, so we're going to, or 45 minutes to work with today, so we're going to go from there. So our goal is to start you on a path of gaining more experience so you can be effective in doing these installations and optimizing a network and troubleshooting it and restoring it. Because we understand, 4RF, we understand that usually when you guys are trying to fix a problem, it's at 2 o'clock in the morning, the power is out, and somebody is complaining that some device is not communicating anymore. So we take a lot of these phone calls in the middle of the night from people asking us, hey, I forgot how to get into the radio, or what's the command to do the following thing. Or I'm stuck. I got this problem where a base station is down and I don't know what's happening. So I'm going to walk you through some of the most commonly seen things that we've experienced and share these with you. Okay, for wireless, we're going to kind of define today what that means. It's probably easier for me to say what it does not include. It does not include microwave spectrum, so we're not talking about anything here that's above about 1 gigahertz, with the exception of some of the LTE cellular solutions that we also do provide. And we're primarily between 135 meg up to about 960 megahertz. And that includes the very popular licensed 400 and 900 megahertz MAS bands, where a lot of SCADA systems live. There are also some systems out there, and probably quite a few of you are using them as well, that are unlicensed, using the 902 to 928, or what's known as the ISM, or Industrial Scientific Medical Band. We also do have a solution for that as well. I'm going to talk a little bit about that too. And we're primarily going to be discussing digital systems. This is really not about voice applications, and primarily the use of these digital systems in things like DA, distribution automation, transmission systems, reclosers, cap banks, sectionalizer switches, subs, all of those other things that you guys are all very familiar with. Okay, so a little bit about the devices and what makes up a radio network. Every system is going to have a master or a base station somewhere in its network. And it'll usually be attached to either a vertical, like what's called a collinear antenna, which is like a fiberglass stick, or a panel or a sectionalized antenna. And depending upon the height of those remotes of their antennas, how far away they are, what kind of terrain is involved, is there vegetation in the path, you're going to get a varying ability to communicate across that distance. And in licensed spectrum, that's usually somewhere in that 20 to 40 to 50 mile range. Under really good conditions where the terrain is perfectly flat and you have a lot of height, you can go much further than that. And we've even seen some applications more so in the West, where we've gone as long as 100 miles between base stations and remotes. But again, that's not the norm, particularly for central and southern Illinois, which is primarily where you as utilities are all located at. Because I know ComEd basically owns the top end of the state. But there's a lot of, even a little bit of munis that are buried within the ComEd territory. I know, like Nashville, I'm sorry, not Nashville, Naperville, and some of the other ones are also small utilities that operate within that larger territory. So we're typically talking about radios, the power supplies that equip them, the antennas, the feed line, and the surge protection devices that keep there from being damaged to the radio. And we're usually interfacing to these radio devices either through an Ethernet connection or a serial, but we also can support things like a USB connection to like a 4-wire RS-485 Modbus, or with our cellular LTE modem, we support fiber optic connectivity as well. And with the electric utility industry, the protocols that we typically experience are DNP3, with a little bit of mirrored bits, some IEC 61850, and occasionally some Modbus messaging as well. And there's typically a lot of other network devices that are attached in the field. Things like RTACs and routers and firewalls and any kind of network management system that you have out there will all be part of this, what we Since you may have heard the term, the term IT. Well, there's also OT, and this is basically an OT for more of a process control IT network. Okay, so a couple of things about some of the solutions that we offer. For RF, we make a product called the XE, and that's more often used by like state police agencies and the federal government, Royal Canadian Mounted Police, and it's point-to-point links to provide high-capacity connectivity between facilities, and it supports a lot of Ethernet or even audio line cards. But probably most often you'll be experiencing, if you do anything with us, it'll be the SR Plus radio, which is licensed. And as I put in here, it says 60 kilobits in a single 12.5 kilohertz wide channel. Well, the same radio, it's the exact same device, is capable of being a base station, a repeater, a redundant unit, or a remote in one package. And every radio is capable of operating at the 12.5, 25, or 50 kilohertz channels and channel widths. And some even can support a 100 kilohertz wide channel. And we do this through the use of QAM, or quadrature amplitude modulation, which allows us to pack a lot more data in the same channel that you used to have. Let's say you had I'll use a good example, MDS 9710 or a SD9 or an SD4, where maybe you were able to do 9600 baud or 19.2 kilobits per second across that licensed channel. We can pretty much straight away, just by replacing the radios, come up with 6 to 7 times more capacity on that same link. And one of the things that we have coming up in the future is another step beyond 64 QAM, where we'll go to 256 QAM. And that's about a year out because we're pending FCC approval. And that'll move our data throughput up to about 80 kilobits per second in a narrowband 12.5K channel. And this radio is specifically designed for SCADA. It's specifically designed for the electric utility industry. It's rated for substation applications. We'd be perfectly willing to share all of our rating information with you. Another radio we have is the SRI, which is the unlicensed radio. That's the one in the lower left-hand corner. And that's a frequency hopper. And you may have been familiar with using MDS as another comparison. The iNet or the iNet2 radio that were frequency hopping spread spectrum radios. Well, ours is a frequency hopping QAM radio, which gives us much better receiver performance than the old iNet or iNet2, where you kind of pretty much had to be better than about negative 85 dB RSSI. We're good down into around 100, 102 dB RSSI. So it's an improvement. And then our newest member of the family is our Aprisa LTE. And it's a dual SIM capable cellular modem. So you can put it on like AT&T and Verizon, or AT&T or Verizon with a private network if you decided that you had a private LTE solution. It also supports things like CBRS. And right now we're pending approval for FirstNet. They asked us to change a few of the menus to kind of standardize the interface. And we're in the process of doing that right now. And it's also equipped with an enhanced security set and very standardized provisioning interface. So it's a very easy device to set up. And it's also rated for vehicular installations. And it has a SPIF connection on the front of it, so you can put a fiber module into this unit. So those are basically the products within our family that we cover. Okay, a little bit going back to the more generic basis of this presentation is everything that we do has to start with a plan. One of the biggest mistakes we ever see a utility making is just going out and buying equipment. And that's guaranteed to be a failure. not a failure in the sense that it won't work, but it's going to be a failure in the sense that then it's going to take you much longer to do. It's going to erode your confidence, and you're going to have unhappy customers usually in the operations center because they're having sites that are going away and a lot of issues, and it may take you months to work through that. And we really don't want you to have that kind of experience. So we would really prefer that if we can work with you in developing a business case for exactly what you're expecting a wireless system to perform and what to do, so we can set some hard goals on what your expectations are as far as throughput and latency and polling and protocols and how many devices per base. We like to understand what those are going to be before we start hanging equipment on poles. And another thing that happens, this is quite often a failure of any deployment, is when you're done and the last piece of gear is hung out there on a pole and it's working, if you haven't changed the way you're doing business of maintaining that system, the project's a failure, because you need to be able to teach your engineers and techs how to maintain the system and how to expand it and recognize when something is going right or when something is going wrong. So those are some of the things that we talk about. And like I mentioned in the bottom part of the article, there's a lot of things that happen to a system that are completely unrelated to the radio, like water getting in coax cables due to poor weatherproofing on the connector ends, or a crushed coax cable because somebody either climbed on it when it was on a tower, or power supplies that are undersized or that are failing, or batteries that are dead. These are all things that affect the communication system and your overall confidence in how it's going to be behaving. Okay, here's an example. This was a bench configuration and testing that was done for Madison Gas and Electric. It was a very simple thing of only 2 remote radios and a base. Actually 3 remote radios and a base. And one of the things we were working out here with this particular utility was their ability to communicate to certain DA devices that they had set up. You can't see it in the picture because they're actually behind this. Certain reclosers and capacitor bank controllers that were using multiple protocols at the same time. So we had to create all of these VLAN tunnels for all of these different services that were going across the radio. And it's a lot easier to do that on the bench than it is to put it out in the field and try to work through it. So that's an important part of a deployment, is to work these things out. And I have a lot of text in here that talks about some of the things you should expect to do during this phase of a project. Okay, little thing about power supplies. You can get yourself in trouble 2 ways with power supplies. You could sit there and look at the current rating on the radio and say, this radio requires 4 amps, which means I need a 5 amp supply. In reality, that's the point where the fuse will blow out, and probably the runtime current may be only as much as 2 or 2.5 amps when transmitting. And when that radio is receiving, that current may be down there around 50 milliamps. So you need to consider the duty cycle of your transmitters and receivers. You may need a lot less power supply than you think you do. I know particularly with that large IOU that's to the north of you, we were going in and just putting in a little radio that drew, 150 or 200 milliamps, and they were replacing station batteries. They tied the entire station battery replacement into the SCADA project, which was probably a good way to get the station batteries replaced, but man, did it drive up the cost and really pushed out the deployment time to get that done. And also too, most of our radios, we can take anywhere from a 10 to 30 volt DC supply, except for some of our base stations, which are available in to be able to take like a floating or a negative 48-volt supply like you see in a server room. So that's another capability that some of our equipment has, is to support different types of input voltages. Or in some cases, we'll go out there and put in a little DC to DC converter to get a radio to come to life. A thing about antennas, when you put up an antenna, it's really important that you keep antennas away from other objects, other metallic objects particularly, because if there are other metal objects near an antenna, it'll change the gain of that antenna and make it less directive. You can also end up with an antenna that is being so manipulated by nearby metal objects that it actually presents a very high reflected power back to the radio. And I'll show you a little bit more about that as we move along. Feedline is a cool word that we use instead of calling something coax. I think we do it because we are honor-bound obligated to include waveguides for the microwave people in there. Otherwise, they feel left out. But a feed line is basically the coax system. And the worst enemy of feed lines is moisture. If you have a type N connector on a piece of coax cable, and you even leave that thing out unprotected for 2 or 3 days in normal weather, it will start sucking up moisture into that coax. Because heliacs, particularly the kind of corrugated copper heliacs, the foam that is inside of them is very low density. It's a very light, foamy material, and it acts like a sponge, and it'll wick moisture up. So you need to be weatherproofing all of your connectors at the time you install the ends. So that's important to do. And the second type of damage that's very, very common is coax that's been crushed. Either it's been rolled out on the driveway when they're building a site out and somebody drives over it with their pickup truck, or they put it up on a tower and somebody steps on a rung trying to climb the tower and they end up crushing the coax at that point. And those cause problems. So those are things also to consider as well. And the third one is also, the next component in the system is the lightning protector, or the TVSS device. And the most common brand out there right now would be like a polyphaser IS50 type surge protector. And we find that those are great for remote locations. But for base stations, because they're a much more critical facility affecting many sites, we usually recommend a different type of protector for base stations, and it's something called a quarter wave stub protector. And there's a couple of companies that make them. Polyphaser makes them, Hubner and Schuer, and a couple other manufacturers that make that type of protector. And really, you need to only concern yourself with that at base stations or repeater sites. Okay. So a little bit about testing the RF side of the radio. And this picture here shows you an Aprisa SR Plus, which is a licensed radio. And it's basically attached through a little black pigtail cable to a watt meter. And in the watt meter, there's a little 5-watt circular slug. And there's a little black finned heat sink to dissipate the heat from the radio transmitting. And below, in the little blue boxes, these are actually the pages that are out of the radio itself, because all of these radios have built-in web pages for setting them up, where we set in this case, we set the power up to 34 dB, which, by the way, is 2.5 watts, no, 2.5 watts average power, 5 watts peak envelope power, PEP power. But the radio is really capable of 37 dB average, 40 watts or 40 dB peak envelope power. So by using QAM modulation, the radio is really a 10-watt radio, not a 5-watt radio, when you consider the peak envelope power of the radio. But in this case, what you're seeing is that on the needle of the meter, that the transmitter is putting out a full 5 watts. And if we took that little silver slug in the center and we spun it, so the arrow was pointing in the other direction, we would be measuring the reflected power, or the power coming back at the radio from the antenna or the load. And the ratio between forward and reflected power gives us an idea of how efficient the antenna system is. And the target for an antenna system is to have no more than 10% of the forward power coming back as reflected. So when you do this in the field on a live system where there's an antenna up on a pole and you're making this measurement, you should not see more than a half a watt of reflected power. If you do, there's something wrong with the surge protector or the jumper cable or the coax or the antenna itself, because that's a measure, that should be an acceptance criteria that everybody recognizes, is that, you know, no more than 10% of the reflected power is a threshold for an alarm. And by the way, our radio will generate an internal alarm if it sees a high reflected power, but it's a ridiculously bad amount of reflected power that will create the alarm. If you ever have a 4RF radio that throws a reflected power alarm, it means you got a really bad antenna system. That's actually come up recently in Texas when they had all the icing that was going on over the last couple of weeks. We had quite a few utilities calling us and saying, hey, I'm getting all these high reflected power alarms and my communications is awful. And what ended up happening, it was ice that had built up on the antenna to the point that the radio was indicating that there was a problem with the ability to transmit. Okay, so a couple of things when you're troubleshooting from the radio. If, let's say, you have a site that is experiencing an issue, some of the things that you want to be able to do is, if you can, across your network, if you can ping the master radio first. This verifies that you have Ethernet connectivity from your SCADA server or from your host across your network, across your fiber, across your routers to get to that master radio. And if you can, the next thing to try to do is to ping a remote. If you can ping a master, but you can't ping a remote, it's helping you narrow down where the problem is. If you can ping the remote radio, can you ping the RTU if it has an Ethernet connection on it? It's not unusual for us to sometimes see bad RTUs that people think is a bad radio. So these are all things that you would kind of do in order of importance. And then there's also additional steps, like you said, do you have connectivity to the master? Can you see the remotes? Are there alarms? Look at the event history. And all of these things take you through the steps to get you closer to figuring out exactly what is happening within the system. So this is kind of a good, important troubleshooting tip. And by the way, this will work with just about anybody's radio. You should be able to, if they have an Ethernet capable device, these steps should all be applicable. Okay, a little bit again, I touched upon this about why QAM is different than frequency modulation. Legacy radio systems have been FM, or frequency modulated, and the transmitter power always stays the same. But when a radio is operating in QAM, it's actually amplitude modulated, not frequency modulated. And depending upon the data that's being sent, the power level will jump up and down. If you were ever a CBer and had a watt meter attached to your CB radio, you would notice that the power would jump up and down when you would, do the test 1, 2, 3, 4 into the microphone and then fall back down. That's amplitude modulation as well. And there's a couple of things in here that discuss about what that looks like on a spectrum analyzer, and why we have to kind of put our radio into a particular test mode to measure power, because it puts a pattern across the radio as a transmitter so we can effectively measure the forward and reflected power. One thing also to note too, because if you do take a system that's currently running FM and you decide to put a QAM radio, and now this is not just 4RF, there are a couple other manufacturers that now make QAM radios as well. You're supposed to modify your FCC license to show that new modulation. And there's a real minor filing fee that the FCC has on it to change what's called the emissions designator on the license. And then they'll issue you a revised license with that new emissions designator. And you need to cite a little part of the FCC code under the comment section, so the examiners there don't get confused as to why you're using amplitude modulation on what's usually been thought of as an FM channel. And again, I mentioned that in this slide. So it's kind of important that if you have the ability to go back and look at these slides later on, that you read through the information. Okay, so a couple of other things further into the whole troubleshooting process. Determine if the problem is related to the master radio itself that's taking out every remote that's associated to it, or if your problem is specific to an individual remote location. Also, is the problem a degradation of performance, or is it a complete loss of connectivity? Is the SCADA system seeing the problem, but maybe you guys have a NMS or a network management system that's not seeing the problem? Or maybe the NMS is seeing a problem, but the SCADA system is not. I've seen it go both ways. Usually a network management system will give you a bit of warning that there's something that's degrading before it has a hard failure. And so that's why we encourage you to have some type of network management system out there on your network. I can't use the word solar winds anymore because it's a dirty word, especially after the hack. But there are other network management systems that are more capable than solar winds. Again, you also want to find out too, is your RTU functioning properly? Is your host functioning properly? You probably want to log into the radio if you can get connectivity into it and look at the event log and see if maybe somebody had innocently gone into the radio and changed a setting on accident. Event logs are really good at helping you figure out if somebody else did something to the network and inadvertently changed a setting that was really important. You also want to consider too, has there been any kind of other network device attached to the system? It's not unusual for us to get that kind of a service call from a utility saying everything's been working great for 6 months, but then over the last 3 days, it's not been working good. And then after a couple of days going back and forth with them, they say, yeah, the only thing we did was to add these extra computers to the network, and the problems seem to happen at the same time. When I'm like, wish we had known that early on, we could have helped you trace that down. So yeah, consider all the other changes that are happening within your network. And if you have the means of collecting a network packet capture, that's really helpful because we can look at that. And also too, realize that the radios store a month's worth of performance data, and that can be downloaded, and we can use that in analysis to find out if there's a problem. And those are also some things that other radio manufacturers also are now including into their products, are event logs that you can save and also performance data that you can download out of the devices. The last one, number 12, came up with utility in Louisiana Friday, where they were telling me that they were having a problem in the middle of the day. Well, when I took a look at the performance logs, I noticed that the building temperature had gotten up to like 130 degrees in the building during the daytime, and it was supposed to be air conditioned. And apparently, after the ice storm, somebody went out there and turned the heater on continuously and left it that way. And then when the warm weather came back in, the building kind of turned into a kiln. And it wasn't killing the radio, it was killing the power supply that the radio was attached to. So I could see the temperature go up and then see the DC voltage begin to experience a problem where it was coming into the radio, because we monitor that too. If you're working in the field and you're out there in front of the radio, in a good radio on a 4RF radio, all the LED colors should be green. You're seeing things other than green colors, there's an alarm or some kind of problem within the device. We put a little button on top of the radio, and I'll show you the picture of that little button. On the SRI and the SR Plus, you see there's a white bar where there's LEDs, and to the right of that, there's a black circle. That's a push button, and when you push that button down and hold it for 5 seconds, the 5 LEDs turn into a bar graph showing you what the RSSI is for that radio. So you can go out to a remote site and you don't have to jack into a radio or monitor pin number 9 on the DB9 connector with a voltmeter to find out what the RSSI is. You can push and hold that button, and that bar graph will change into a bar graph with green, yellow, and red colors, and a little chart that comes with every radio telling you what the received signal level is at that site. So it's a very handy tool. After 5 minutes, the radio reverts back to normal operation of the LEDs. So, excuse me. Okay. That's again pushing the test button number 2 on the page. Checking your cabling to and from the radio. Also making sure your feed line has not been stolen by copper thieves. It's happened. Make sure that the DC voltage is between 12 and 30. The radio is happy anywhere in there in between. But if you exceed 30 volts and you go to 30.1 volts, the radio will blow its internal fuse. And fortunately, the fuses in the Aprisa, we have, you can open up the case on the radio and you can see the 2 fuse holders. We also include 2 spare fuses inside of every radio under a little black plastic cover. So if you blow a fuse on a radio in the field, there's spares right in the radio. In fact, if you picked up a brand new radio out of the box and held it next to you and shook it, you could hear the rattling of those 2 little fuses, spare fuses, in their little plastic holding cup in the radio. So if you exceed voltage, you will pop a fuse. You want to be able to log into the remote radio and do things like checking the event log file and maybe even getting the performance logs out of the radio. You can download them. When you're in the web page of the radio, it'll present you a view that, because it is a web browser, you can use Chrome or Firefox or Explorer, whatever the new Microsoft browser is, and you can go right into the IP address of the radio and pull up a web page. And from there, you can download files, and it saves files to your computer just like you would normally grab music off of a web page on the internet. You don't need FTP or TFTP to grab these files. You can save them directly to your desktop. And again, if you do download those event log files or performance logs, and then you have to call 4RF for help, we're going to ask you for that information anyway, because we use that to analyze what's going on in the radio. And I'll show you a picture of that as well. Again, you can also try to reboot the radio, power cycle it, and see if it clears. If it doesn't, you can take a spare radio and you can load that configuration file from that remote into the spare and get yourself back up on the air. and then bring back the old radio for further testing. I'd say of radios that are returned back to us for some found problem, usually after we factory default the radio and retest it, we find no problems 80% of the time. So it's a pretty bulletproof little device. Okay, here's a little bit about performance logs. And I kind of hinted at this on the previous page. We record all of this information within the radio, and we store the data in two ways. For the last 24 hours of operation, we do a sample of the minimum and maximum values of about 100 different parameters that are within the radio, and we save those on a 15-minute sample. And we also record on a daily sample of minimum maximum values for a month. So this allows us to go either look at what happened in the previous 24 hours with some pretty good detail, or we can look at longer trends over a month to see if there's things that are happening on weekends or the evenings or the what's happening there. Those files there's nothing particularly special about them. They're comma separated variable files. Microsoft Excel will even allow you to import CSV files and create tables out of them. And if you're a Microsoft Excel wizard, you can make graphs like we do. In fact, these two images below are actually the graphs. And they're showing us things that are pretty relevant for the way this system was behaving. This is actually a real customer, another one in Louisiana, that was experiencing a problem. And what the big issue that was happening here is that they were losing a tremendous amount of data. And on the left graph, it's the red bars. And that's packets that have been lost, received packets that were not received by the base station. And that's horrendous, because normally we should never receive packets that are lost. It'll be down there like less than 1%. But for these kind of numbers that they were seeing here, where they're so high, they're getting packet loss in some cases upwards of 20, 30%. And we were able to go back and look at another one of the other configuration files on the right-hand side, and we were able to see the orange colored solid line is the signal to noise ratio. And the dashed orange line is what the signal to noise ratio is normally, and the solid orange was what was happening intermittently. In other words, it would have a really good SNR of around 30 or 32 dB, but then suddenly it would drop down to 15 dB momentarily. And we figured out what the problem was, is they had put up a second base station a couple of miles away, and it was on the same frequency. So the bases were colliding with each other, causing SNR issues. And when the SNR, the signal to noise ratio, was bad, we were experiencing packet loss. And because these were SRI radios, or the unlicensed radios, we were able to break up that 400 channels of 902 to 928 megahertz and give each base station its own block of 50 channels to work on, so they wouldn't interfere with each other. And that solved their problem. And again, this was found just by using performance logs. I talked a little bit about doing network traffic analysis and capturing the network traffic. And here's an example of another one. This was actually in Charleston, North Carolina, or South Carolina, yeah, in Charleston. I went out there for this one. But the problem was happening is you see all the black lines on the page, and that's the SCADA host resending requests about every 70,000th of a second. When I talked to their SCADA people, they said, oh yeah, well, we're only polling once every 5 seconds. We can't understand why the system's not working good. Oh, 5-second poll shouldn't be a problem. And yeah, I agree with them. It shouldn't be a problem. But until we did a packet capture and looked at what was really happening, were we able to find out that there were so many reattempts by the host to get data that it was basically killing the entire network. And they were using a Modbus system because this is actually a water utility. And while it was working with only a few remotes on the master, it would not allow them to grow the system. And that's where they were trying to get to next, was they had like 5 remotes on this master, but they wanted to bring it up to about 30 remotes. And when they started adding additional devices, it started taking down the first ones that were there. So packet capture allowed us to look at that.
Real quick, Tisha, we did get a question.
Sure.
I don't know if it's on this slide or a previous slide. Is this all specific to the 4RF radios? They said I get the general troubleshooting for any device, but is any of this specific to your devices, or is this just in general?
Performance logs are definitely 4RF. I think 1 or 2 other manufacturers also have the ability to look at performance logs and download them out of the radio. Network traffic can be anybody's radio because it's an Ethernet function. But most of these primary steps here, other than pushing the test button, on the 4RF radio, that's anybody. That the same rules apply on this list of 12 like I have up here. 11 of them still apply. Performance logs, I'd say there's 2 or 3 manufacturers that have a somewhat similar capability of looking at this data. Network traffic is anybody with an Ethernet connection can look at this type of information. In fact, if you do a thing like a network traffic capture and you want let's say it's one of our systems, you can send us this file and we can help you identify traffic flow issues. And you probably could do the same thing with GE, or I think GE will probably want to charge you for it, I'm sure, because their systems group is for profit. But some of the other companies will do this for you as well too. Some for free, some not for free. I hope that answered that question. But I'm going to continue through. Here's an example of interference from a legacy system. And you can see where the kind of teal colored graph was an existing transmitter that was brought. And if you see the gray box in the middle, that is the officially sanctioned FCC channel for this system. It's 12.5 kilohertz wide at 451.400 megahertz. And you have to stay within that gray box. And you can see that the legacy system was the teal colored graph, and it was actually wiping out 4 channels in addition to using its own. It was taking out 2 channels on either side of the bar graph, of that graph. What do I do? Let me get back to where I was. It was taking out other channels. And the graph in red, that's a 4RF radio. We stay within our boundaries and stuff. But yeah, you definitely can see that some of these other devices that were out there. Actually, the teal graph, I can say this and not get in trouble for it, that's CalAmp. The purple and the blue graph was GE, and the gray and the red was 4RF. All 3 devices operating on the same frequency. So yeah, you can kind of see that there's a little bit of a difference in how some of these devices operate. This was actually at an electric utility in Tennessee. They were doing a multiple radio system test shootout. So, okay. Again, going back to graphing, and this is a graphing this is a 4RF thing. This is within the radio itself. We have the ability to do graphing, but we can kind of see some behaviors that are where we're getting some intermittent interference across the system. And what this was doing on the graph on the right-hand side, it was actually, you see this kind of like sawtooth pattern on the right-hand graph. This was for a electric utility in South Georgia, in Warner Robins, Georgia particularly. And they're getting interference from a local television station. This is a 200 megahertz system, and they were getting interference from, like, I think channel 7 or channel 9 on the TV, because their master station antenna was at 300 feet elevation, and they're only like 50 miles away from Atlanta, and they were getting whacked by Atlanta television stations. So this was one where we had to put a filter in to solve the problem. But then here's some other examples of intermittent interference. This was out in Idaho. Again, you can see that there was some interference from other transmitters that were out there too. They were kind of hitting us pretty hard. And the graph on the right-hand side, you see those little boxes that are kind of like jumping up and jumping down? That's actually HDTV. That's what an HDTV carrier looks like. And each of those boxes is a different channel. And our desired signal was right in the center where my cursor is right now, if you see the cursor. And we were getting interference levels of, negative 60 dB, where we had remotes that we were trying to talk to that were coming in at negative 100. So we were well below these interference sources. Again, this was one where we required a filter to get rid of this interference. And another problem, again, is something called co-channel. And this was with the utility, Idaho Power, where they have 700 megahertz system, no, 200 megahertz system. And they were allowed to create their own channel spaces. And the first one here is a 50 kilohertz wide channel in the center, and then next to it's a 25 kilohertz wide channel. They were too close to each other on a self-designed system, and it was causing a degradation of both bases. So again, a spectrum analyzer is a pretty useful tool for finding these types of things. Again, this is applicable to anybody's radios, not just 4RF's radios. And again, here's some other issues involving co-location, where we have, you can see the graph. These graphs show you what is going on before and after a filter. The red graphs in all three of these images are what the signal was like without a filter being in place. And the black line shows that once the filter was installed, what happened to the interference. So there's a window up here in the upper left-hand corner. That's a 928, 952 MAS network. The one in the upper right-hand corner is a 700 megahertz system. And those two big carriers on either side, the one on the left side, that's Verizon's LTE network. And the one on the right-hand side of the center is actually FirstNet. And those were strong enough that they were interfering with our tiny little SCADA signal in the middle. So when we installed the filter, it took those interferers down to the black line. And we did not lose anything in the center other than maybe about 2 or 3 decibels of insertion loss, but it radically improved performance because we took out the interference level. So these are just some of the things that kind of show you that you can do with a spectrum analyzer to look at something before and after trying or testing out a filter. And again, this is another example of that type of thing where everybody is operating according to their rules. In the center is the 700 megahertz band, with the little one diamond is being our channel, and you can see our little tiny carrier in there. And then Verizon LTE, AT&T LTT, and the one that says UNC LTE is actually T-Mobile. So those are the three LTE carriers. Then you see FirstNet, and you see the control channels that the cellular companies are using. And then the subscribers are basically the handsets, or what your cell phone transmits. Because the base stations transmit on the low side and the handsets transmit on the high side. So yeah, filtration really, this kind of helps you identify filtration, and also determining what kind of filter should you put into a system. This was actually something out of Wireshark. This was not a 4RF radio system. This was a mesh network. But looking at the Ethernet traffic, and this is over from about 5:50 in the morning till about 5:30 at night. And you can see the black line where it starts to peak up around, between 7 and 10 o'clock in the morning. And those are report by exception messages that the remotes are sending back to the host using DNP3. So there was a bit of an up peak in traffic, and that's the blue curve that you see there, and that's normal. Then after the morning curve goes away, it comes back down again. But then they had this hard failure right around noon on this system. And you see that it spikes up suddenly. You see these giant black spikes, and then it just buzzes for hours until finally the problem goes away when somebody resets the router. This was a failure of an IPsec tunnel. They were using IPsec, and they had a network diagnostics tool that would do a poll of every Ethernet device in the system at noon every day. And it did not pace out those polls for all of those network devices. It did a massive blast, like a lightning blast, of like 3,000 polls in less than a second from their network management system. And when it hit the SCADA network, it would take the SCADA network off the air because the IPsec tunnels would collapse. And when they collapsed, they had a real hard time reconnecting until somebody recycled the router. So yeah, you could see this was you would think that this was caused by the SCADA system, because people would be going, I lost SCADA to all these sites, what's going on? In reality, it had to do with the IPsec tunnel, which runs at a layer above the SCADA system itself. So yeah, the network can cause problems for us too. And I kind of talked a little bit about transmitter mask before, but I'm not going to go into this very much. Here's an example. This is actually at a Army base. The Yagi antenna for this little station right here, they said it would never work. And I went out there and took a look at it, and it's because the antenna is pointed right at the side of an aircraft hangar. Of course it could never work. It was trying to go through steel. So yeah, this was for some reason, they said for some reason this site doesn't work, and nobody was able to kind of figure that out for like 10 years. Same utility, or the same place. By the way, this was Fort Polk in Louisiana. And you see how the antenna has this distinct bend to it? This was at one of those places that simulates like Iraq, where they actually have Iraqi road signs everywhere and people are carrying live weapons. Soldiers were bored and they were using the Yagi antenna as a chin-up bar. So they bent it. And we were having problems because I also did some damage to the coax as well, but I just had to grab the picture of this. Some of these base station installations, they don't necessarily just have to be a single omnidirectional antenna. You can have multiple base stations operating. In this case, there's 3 base stations in that rack. Those are the ones with all of the solid little green lights. Those are redundant chassis, by the way. So there's 2 radios in there with automatic failover if one of the radios goes bad. And each of those radios is attached to a different sector on the panel antenna, creating 120-degree coverage areas. Gotta watch my time. I'm running late. Okay, so yeah, I just wanted to point that out to you again. And again, here's a little bit more about Verizon overload and managing interference. The use of filters to eliminate problems, and you need a well-designed filter to go after certain issues. Again, a little bit more Verizon interference at 700 meg. Bad antenna. Copper braid being crimped in place with a nickel-plated brass ferrule onto a piece of aluminum tubing covered with weatherproofing that didn't weatherproof anything at all. So yeah, this was a bad antenna. Not something we sold, but was sold by somebody else. A little bit about what happened with what's called passive intermodulation on a spectrum analyzer. This is caused by a loose coax connection. The type N connector was loose. Tightened up the connector, the problem went away. And that's the end of my presentation. Are there any questions?
Yeah, Tisha, we have had a few more questions come in, and we'll try to get to those real quick. We've got a few minutes here. We can still do it. So, can these troubleshooting techniques be used on radios from other manufacturers?
Absolutely. I could probably use a couple examples. GE has a product that's pretty good about having network capabilities and diagnostics features. Some of the others, not necessarily so much. I also know some of the other manufacturers are kind of dropping their SCADA products. And on legacy gear, there's going to be less support. There may be event logs, but there probably won't be much to do with performance information.
I think the last question we have is, what makes the 4RF radios different in regards to troubleshooting aids?
Oh gosh, the ability to keep things like performance logs and pull down event data and look at things graphically, and even if you don't have a network management system, you can still go in and do many of these things just with the browser on your PC. I think that's one of the real big strengths to the 4RF solution, and that 4RF is a radio company first and not really a network company. We design radios. Any other questions?
I think that's all we have. Tisha, we want to thank you for your time today. It's very informative. Lots of good information in there.
Okay, well, I'm glad to be of service, and thanks a lot.
If you, I think you had your contact information up there, and if any of our participants didn't get a chance to jot that down, if you'd like to reach out to Tisha, get in touch with us, and we'll make sure we point you in the right direction, get you hooked up with 4RF. Coming up this afternoon, we have our, I believe this will be is this our 40th?
Yep.
Our next webinar is up at 2:30. Our 40th webinar in the third series. We're looking forward to that. That is going to be on, sorry, I lost my notes here. Voltage optimization and effects of DERs on the grid. That one is eligible for engineering credits. So if you register for that, I'm sure Brian will make sure he gets that out to you. If you haven't registered for it and you'd like to, reach out to Ashley. She'll make sure she gets you registered for that upcoming webinar. And that concludes this webinar series. Thank you very much. Thanks, Tish. We appreciate it.
Thank you.
You're welcome. You're welcome. Okay, bye-bye.